Welcome from my side. My name is Ben Schneider. I am a researcher at Fortiss in Munich, Germany, and a PhD student at the Technical University of Munich. Our paper, which was created in collaboration with Huawei, is a proposal for time-aware scheduling in wireless industrial IoT environments. So let's dive right in. So when you compare Wi-Fi with wired technologies, you have specific advantages in Wi-Fi, for example, the flexibility. So if you consider reconfiguring your plant, it's just easier when you don't have to deal with wires. Also, there are scalability advantages. If you want to add more devices to your network, you can easily extend your Wi-Fi network with mesh networks or with multi-IP scenarios. And of course, also if you consider moving clients, like in a warehouse scenario where you have different AGVs transporting goods from A to B, you would, of course, not use any kind of wired technology, but need wireless in order to facilitate this movement. Additionally, modern Wi-Fi can compete with the speed of Ethernet networks. So that's kind of the speed of wireless of Wi-Fi, and Ethernet is almost the same. Wi-Fi also offers some very interesting new enhancements and also what we think the technological basis for deterministic communication. For example, the new media access mechanism that is called OFDMA. But Wi-Fi still lacks deterministic scheduling mechanisms, so that's the target of the paper. Where do we work? So what I brought here is a very simplistic topology of a network. On the right-hand side, these blue devices, you have a TSN domain, a time-sensitive networking domain, so that is wired Ethernet, with a TSN switch and two end devices, either talkers or listeners. This TSN domain is extended, let's say, by an access point with a Wi-Fi 6 domain that you can see on the left-hand side with specific Wi-Fi 6 capable stations, which are associated to the access point, of course. In TSN, we have specific scheduling mechanisms which already facilitate deterministic communication. For example, the TSN Time-Aware Shaper, the TAS. The TAS is a TDMA-based mechanism widely used in the industrial automation domain. On the other hand side, in Wi-Fi, we don't or do not yet have these kind of explicit scheduling mechanisms for deterministic communication, but Wi-Fi 6, as said, offers these new features, for example, in the frequency domain with OFDMA resource units. So the main idea of OFDMA is that you do not grant a specific station, for example, access to the whole channel. I mean, you can still do that, but you can also split up the channel into these smaller resource units, as they are called, like these frequency chunks, and then transmit within these resource units simultaneously. So that is very interesting also for traffic isolation, for example, which is needed for deterministic communication. And on the other hand side, we have the time domain extended features, for example, with target wake time. So the initial idea of target wake time is that you can actually save battery power by putting the interface cards of battery powered devices to sleep and just wake them up when they should communicate with their access point. That's the overall idea. And the main challenge and the main target is kind of to extend these features that we already have and which are working in wired to the Wi-Fi domain, such that we can, in the end, hopefully communicate between wired and wireless in a seamless manner and, for example, fulfill latency or jitter requirements when sending packets from TSN to Wi-Fi 6 and vice versa. So the idea is to create scheduling mechanisms or extend the features in Wi-Fi on the access point and the stations. That's where we work. The overall goal is to optimize time and frequency domain in OFDMA-based Wi-Fi to better support real-time industrial applications. So that also the background basically for the work is the industrial automation domain and the flexible factory. A little bit more detail on the wired TSN TUS, the time-aware shaper. Again, as said, it's a time-triggered approach, a TDMA-based approach. So a little bit simplified idea is that you would just split up your time into cycles of equal length. These cycles are repeating over and over again, and then you would have these kind of slots or priority windows reserved for specific kinds of traffic. So for example, here in this first blue window, only traffic with priority number 1 is allowed to be transmitted, and the others of course have to wait. So this is a classic approach for isolating traffic from each other, and also to modify, of course, the latency, because depending on where the slots are, you can, of course, influence the latency of the packets. In Wi-Fi with TWT, we have a kind of a similar thing or something that can be tweaked in that direction. However, TWT was initially designed for, as said, power-saving purposes. So the idea is you have a battery-powered device, you just wake it up when it needs to communicate, and otherwise it will be asleep. So that's what you can also here see in these figures. TWT was extended. So it was created in .11AH, so previous Wi-Fi standard, and was now extended with additional flexibility in this Wi-Fi 6 standard in .11ax. You, for example, have different kinds of options and service period agreements that you can use. So service period is just kind of this time when a station wakes up and transmits or receives and then goes to sleep again. So you can have individual TWT service periods, which is kind of a single station waking up for communication with the access point and then going back to sleep again. You can have broadcast TWT agreements where you can basically wake up several stations, a defined number of stations basically, and have them communicate simultaneously. Or you could have the last option, which is kind of the opportunistic power saving mode, where you just define specific wake up times, but you do not define which stations have to wake up during that time to transmit. The stations would just decide on their own and then randomly wake up during these times and try to get access to the medium. So what we want to do is we want to kind of tweak what we have in TSN. So this is what you can see here again, an example of such a time-aware shaper, task cycle, a schedule. In the automation domain, you would typically have these different kinds of traffic types. And for simplicity reasons, we just took an example that has all these types and all the different slots with the same length. So you would have, for example, isochronous cyclic traffic, or in the later part of the cycle, also events or configuration and diagnostics data. And what we want to do now is to map this kind of functionality in wired TSN to what we have in Wi-Fi 6. So we could, for example, just very naively go ahead and say, well, we just map what we have in TUS in wired to these Wi-Fi 6 service periods and just wake up the specific stations during their priority window and make them transmit and then go to sleep again. Or actually, if one station has multiple traffic types to be transmitted, it would wake up in different points of times during this cycle. The problem with this approach is that it, of course, wastes bandwidth for event-triggered traffic. So if you can imagine that events might not happen in each of the cycles. So in some cycles, you would actually not have any kind of event-based traffic to be transmitted, and thus you still reserve the time, the bandwidth basically, but no transmission would be going on. So you would waste bandwidth in the end. This problem is known as over-provisioning. In the industry, this over-provisioning problem in TAS is currently discussed by kind of splitting up the schedule in two parts. The first one would be for cyclic traffic, so this kind of static approach where you have these recurring priority windows, the classical TAS approach, let's say, TDMA-based approach. And the second half where different priority or different traffic types would share the resource and access it based on a different kind of scheduling mechanism that is a little bit more flexible. So it's just on demand, let's say. In Wi-Fi, we could do something else. Okay, for the recurring and time-triggered traffic types, you can just again directly map these priority windows to the TWT service periods. For the more flexible part of the event-triggered traffic types, we could have some on-the-fly and during runtime negotiation of these TWT service periods. So that's what you see here in the light green. In this light green phase, so the idea would be, okay, the access point checks the buffer status if there is, for example, events and best effort traffic to be transmitted, like in this example, and then it would schedule specific TWT service periods in order to really schedule these kinds of traffic types and the stations to wake up and transmit their traffic. So that would also be possible in Wi-Fi. And again, the idea would be to have this static approach, the static mapping for time trigger traffic, and something more flexible and on-demand scheduling of opportunities during the event-triggered part, let's say, of the schedule. What we did is we implemented this first, the static approach, so this idea of directly mapping the priority windows from TAS to what we have in. So what we implemented is the static approach, so this mapping of priority windows and TAS to the TWT service periods in Wi-Fi. So this is our topology that you can see here, some TSN talkers, TSN switches, of course, which were Huawei prototypes. So again, this project was in collaboration with Huawei. And then an access point in Wi-Fi 6 access point based on open source drivers on the Intel IWL Wi-Fi driver, and also the end devices based on the Intel hardware and Intel open source software. On the right-hand side, you can see the configuration of the switches and of the service periods in the two stations. After another wake up, transmit, then go back to sleep, and then the other station waking up and transmitting and going back to sleep. And in this way, we can kind of isolate the different streams, one critical and one best effort stream, in a way that they do not interfere with each other. The experiments are so far not super convincing, we have to say. So we did 4 kinds of experiments. The first one is always, so what we measure is always the latency from these kind of TSN talkers over the 3 hops to the end devices, the wireless stations. And the first thing that we did is to measure only the latency in the wired area. So just from the TSN talkers to the Wi-Fi 6 access point, that is about 307 microseconds. Then we measured the delay, the latency from the endpoints, the wired endpoints to the Wi-Fi endpoints. So from the BeagleBone Blacks on the right-hand side to the stations on the left-hand side, which was roughly 14 milliseconds. No TWT approach or any scheduling enabled. It's just like first come, first serve. And then we did 2 experiments with TWT, basically one with only one stream that is transmitted, and then the second one. And what you can see here is that these latencies on average were 48 or 46 something milliseconds, which is of course not what we expect to have, our current idea or our current target for latency would be below 10 milliseconds from a wired talker to the wireless listener. So in the end, the issue was actually with the openness, let's say, of the driver. The performance bottleneck was caused by the low-level firmware. So basically this part of the firmware which takes place of the time-critical things, which is not accessible and not open source. So you can basically have access to the upper part of the MAC layer and everything that is above. But the lower part of the MAC layer and the respective functionality, for example, for us, the wake on wireless LAN features were not accessible and such could not be optimized. But still, we think that TWT kind of is promising to be used for time-triggered scheduling or for TDMA-based scheduling in Wi-Fi. We have to further optimize the implementation or just use another means of evaluating, basically. If you are interested in joining forces, we at Fortiss have a demonstrator that is the TSNWiFi demonstrator in our Fortiss IIoT lab. This demonstrator is, or the part of the demonstrator that I've shown you before, is basically embedded in this kind of bigger demonstrator. So the idea is that we evaluate two main things in a flexible factory scenario. These two objectives are time synchronization, wireless time synchronization between wired and wireless domains, meaning Wi-Fi 6 and TSN. And on the other hand, of course, the deterministic scheduling part, which I just shown you before. If you want to collaborate, the demonstrator is open and accessible, so you can visit it in Munich, of course, and we can give you a tour, and we're super happy about discussions. The code can also be accessed upon request, and for that, please contact either my boss, Ruth Sofia, or myself, Ben Schneider. Conclusions and future work. What we've shown is kind of a concept for a static and flexible scheduling approach based on the target wake time feature in Wi-Fi 6, including a proof of concept implementation of the static approach that we've shown using open source drivers based on Intel IWL Wi-Fi. The initial results still have to be improved, but show that TWT is a promising feature to realize time-triggered scheduling in Wi-Fi. For future work, we still want to do experiments using multi-IP scenarios and topologies, and of course maybe also to swap the hardware and use, for example, a software-defined radio platform for experimentation to overcome the performance bottleneck. Thank you very much, and happy to answer your questions.